All right, we're going to get started with the third and final midterm exam review. We'll be back here 1 week for today to finish the final exam review. That should be a shorter session since we'll get through about 2/3 of that during the week. One thing that I'll ask today, there's not very many of you here in person, so it shouldn't be a huge problem anyway, but last one went kind of long, which I'm fine with. If there's a lot of questions, I'll stay as long as I need to get them answered. But I think what would be helpful is if you're going to ask a question about a problem, wait till the end of the problem to ask, because sometimes you'll ask something in the middle that I'm about to say anyway. So it'll keep things moving a little bit better if you're able to just hold your questions until I'm finished going through that. And then anything that you don't understand about that specific problem or anything related to that topic, please feel free to ask. I'm not trying to discourage that. Just want to keep things moving as best as possible. All right, so the first question here, so remember that this exam is on chapter 7, 8, and 9. As this review sort of indicates, it's definitely more heavily skewed towards chapter 7 and 8 because it only includes about half of 9 anyway. And so it goes roughly in the order of the topics. So the first half or so of the question, or first 9, I think, are going to be dealing with chapter 7 material. And so this one here deals with calculating the work when a sample of N2O expands from 3.75 to 8.25 liters against a constant pressure of 957 torr. So there's only one situation where we learn how to calculate work, and it's going to be using this equation here. So it's when we have this exact situation, a gas expanding against a constant external pressure. And so as long as the pressure that it's expanding against is non-zero, then the work will also be non-zero. And so in this case, those are the two things you have to multiply together. There needs to be a minus sign out front. And delta V, of course, is the change in volume final minus initial. So for a problem like this, it's a relatively simple equation. It usually just comes down to plugging in the numbers that were given. So the external pressure is 957 torr. Now you'll notice here that the pressure's in torr, but all the answers are in liter atmospheres. So we'll have to convert the pressure into atmospheres first. This is something we didn't learn until chapter 8, but it's all going to be fair game for this exam. So to get pressure into atmospheres, we have to take the pressure in torr that we're given and divide by 760. So 1 atmosphere is 760 torr. And so that comes out to 1.26 atmospheres. So usually when you're doing this equation, work equals minus external pressure times delta V, you'll put the pressure in atmospheres initially. And then, of course, depending on what your answer choices units are, you may need to change that at the end. But we'll start with atmospheres in almost every case, and then we'll just have to do delta V, which is final minus initial. So it's going from 3.75 to 8.25. So 8.25 is the final volume, and 3.75 is initial. And so when we multiply those out, we get negative 5.67 liter atmospheres. And that's the units that the answer choices are in. It's not the most standard unit for work or energy, but it's the one that we're using here. So we don't have to do any further conversions, and we can just select choice B. Now the conversion that you might need sometimes, I think it's usually stated if it's needed, but just in case it's not, remember that 1 liter atmosphere is equal to 101.3 joules. So a lot of times in work problems, any problem involving energy, we would need to convert the answer into joules or kilojoules, and this is the conversion that will get you there. You might wonder, how do I remember this conversion? Well, if you forget it, there is a way to help you recall. So if you're on your periodic table here, we have a bunch of constants listed at the bottom, and we have the one that's going to be relevant to this is the universal gas constant R, which has 2 values here. Okay? All right, so here's R, and it has the value in liter atmospheres, which is what we typically use for gas law problems, and then the value that we introduced and use in some context in chapter 9, which is in joules. If you divide those two numbers, that will give you 101.3 joules per liter atmospheres, because they both have mole Kelvin in the denominator. So if you forget that conversion and you need it, just divide the two values of R that are right here on your periodic table. That's joules, that's liter atmospheres. That will give you the conversion factor between them. All right, but it is 101.3, which you'll want to remember. But we don't need it here because our answers are in liter atmospheres, so we stop and just report the number. And it's also helpful to think about it conceptually. It is negative because we're expanding. Anytime we're expanding a gas, that means the gas is doing work against the surroundings. Whenever something does work on the surroundings, it's going to be a negative value for W. All right, so I think that takes care of that one. Any questions on that question or that topic in general? Yep.
Are there any other like main conversion factors we need to know?
So the conversion factors, I mean, two of the main ones are given here, so torr to atmosphere, and then as I said, this one. The other one that will sometimes come into play, and I think it might actually come up in the next problem, but I'll just state it here since you asked, is calories to joules. So this is another common energy unit, and it's 4.184, which is, again, another familiar number because it's the specific heat of water. I think on most of the exam problems, any weird conversions like this you needed will be stated for you, but these are ones that you probably should know just to be safe. These three that are all listed here now. And we'll see maybe if others come up during this review, but I think those are the three that come off the top of my head. All right, any other questions?
So when it's compressed, will the work be positive?
Yes, so when you compress a gas, that means the surroundings is doing work on the gas being the system in that case. Usually when you're talking about expansion or compression of a gas, the gas is the system, and when you do work on the system, then you're going to have a positive W, is correct.
That PX is an external?
Yeah, that's external pressure. So there are other situations where you could calculate work. We didn't really talk about any of those. If you've taken calculus, technically the work is the negative integral of pressure times pressure with respect to volume. So if you know calculus, this is really where this all comes from. But we're only doing it for this specific situation where, say, constant external pressure. In that case, it's this simple equation here. Okay. All right, if there's nothing else, we'll move on. So the next one is another relatively simple equation that's related. So it wants to know what is the change in internal energy in kilojoules when a system absorbs 965 joules of heat and has 456 calories of work done on it. So in problems like this, whenever you see change in internal energy, remember that the symbol we use for that is delta E. Delta always means change. And when we have delta E and we're talking about heat and work as being part of that, again, it's just one equation that should come to your mind. That's a very simple one. Delta E is Q plus W. Now the trick in these problems, because usually Q and W are going to be given to you directly, but the trick is, first of all, to make sure that they have the correct sign, because usually the sign is not attached to the number in problems like these. We have to use the wording of the problem to tell us if we should use a negative or positive Q and a negative or positive W. And moreover, we have to make sure they're in the same units before we add them together. Now we're looking for an answer in kilojoules. So I think initially we could probably add them together in joules, or we can convert them both to kilojoules right off the bat. But we have to make sure that Q and W are both in the correct unit. Okay, so what we have here is for Q, let's look at the wording in the problem. The system absorbs 965 joules. So whenever heat is absorbed by the system, that means it's going to be positive. If heat was released, it would be negative. So that means we need to have a plus sign in front of our heat term, which is given in joules already, so we don't have to convert it. We could convert it to kilojoules, as we said, but we can do that at the end also. So we're going to use positive 965 joules for heat. And then for work, we see that the work is done on the system. So when work is done on the system, that means it's going to be positive. So remember, these are always with respect to the system that we're studying, and we don't really specify what the system is in this case, but work is done on it, whatever it is, and that means the positive value for work. Now work is given to us, though, in calories. So again, the conversion that I just covered on the last page, which is the specific heat of water, also the same number, 4.184 joules in 1 calorie. And it's not a coincidence that that's the same number as specific heat of water. That's because the specific heat of water is defined as 1 calorie per per gram degree Celsius, which is also the same as 4.184 joules, the more conventional number we use. All right, anyway, what that comes out to, though, is 1908 joules, so we're going to add that on. So before we add the two numbers, they have to be in the same unit, whatever unit we choose that to be. So it's going to be 2,873 joules. And then to get to kilojoules, which is what the answer choices should be in, we divide by 1,000, and we'll report it as 2.87 to 2 decimal places. All right, and so that matches up with choice A up here, 2.87 kilojoules. So again, in these types of problems, I think a lot of people sometimes forget about this equation. They see, change in internal energy or delta E, and they think it's going to be some complicated calorimetry problem or something. But really, remember, there's this relationship here, which is really the definition of delta E. The two different ways that we can change the energy of something are in terms of its heat or its work, and it's going to be just adding two numbers together. The key is to make sure that you use the right signs and the right units when you're adding them, and you'll be good to go. So any questions on that or that topic? Okay. All right, and then the next question, which is going to be a fairly typical thing you'll see on an exam, is a conceptual question dealing with heat, energy, enthalpy, things like that. So again, those major chapter 7 topics, this is more conceptual in nature. So it's a reaction between HCl and NaOH, which we've studied a lot in chapter 6, is exothermic. And we want to know which of the following statements is correct. All right, so when we're talking about exothermic, remember that what that tells us is the sign of delta H. So in A, the answer choice A says delta H is positive, but that's the opposite of what it should be. So in an exothermic reaction, delta H should be negative or less than 0. So that's going to be incorrect. We're looking for the correct statement here. So exothermic means negative delta H. The next one is that the enthalpy of the products are greater than the enthalpy of the reactants. So when we're talking about delta H, even though we don't really calculate it in this way, what it really means is, again, delta means final minus initial, the change in something. So in a chemical reaction, when you're talking about delta H, the initial state is the reactants, the final state is the products. So if we're talking about delta H, we can think of it as enthalpy of the products minus reactants. We don't typically calculate it this way in terms of absolute enthalpies, but that's what it really means. And if it's exothermic, as we said, it has to be less than 0. So in order for the enthalpy change to be less than 0 to be negative, if we rearrange this, it means that the enthalpy of the products have to be less than the enthalpy of the reactants. So if we move H reactants over, we get this inequality. So anytime you have a negative enthalpy change, it means the products have less enthalpy than the reactants. The enthalpy is decreasing during the reaction. So this one is also incorrect because it states that the enthalpy of the products are greater, but they should be less than the reactants in an exothermic reaction. Choice C, the temperature of the surroundings increases. So again, another thing about what it means to be exothermic. Exothermic means that heat is released, because delta H is a measure of heat at constant pressure. If delta H is negative, that means heat is released anytime Q is negative. So when heat is released in an exothermic reaction, that heat gets released to the surroundings, and the surroundings temperatures will increase. So whenever you have an exothermic reaction, the temperature of the surroundings increases. Think about when you burn something, right? Burning is an exothermic process, combustion. And when you burn something, the temperature increases around it, and that's because you're releasing heat to the surroundings. So that one would be correct, because here it says the temperature of the surroundings increases. So that should be our correct answer. Let's go through the other two to make sure that these ones are also incorrect. So here we're talking about the bonds in the products being weaker than the bonds in the reactants. So the other way that we learn to estimate delta H is in terms of the bond strengths. And remember that when we're doing it in terms of bond energies, we take the sum of the reactant bond energies. We're going to have a problem like this later. But we can take the sum of the reactant bond energies and subtract the product bond energies. In this case, it's reactants minus products when we're using bond energies. And so for an exothermic process, which is less than 0 for delta H, again, rearranging this, what happens is we see that the bond energies of the products have to be greater than the reactants. I'm not going to write the whole thing out. But in an exothermic reaction, you have stronger bonds on the product side than the reactant side. And again, this one is the opposite of what should be the case. So again, another way to think about that is when you do a chemical reaction, when you form chemical bonds, you're forming attractions between electrons in the nuclei, you're releasing energy. And so if you have an exothermic reaction, the bonds that you form on the product side need to be stronger. They need to release more energy than the bonds that you broke on the reactant side, which you have to put energy into. So that's another aspect of exothermic reaction. And then choice E here is sort of the opposite of choice C. The reaction absorbs heat from the surroundings, but again, if it's exothermic, delta H is less than 0, delta H is equal to the heat measured at constant pressure, and so in this case, heat has to be released anytime you have an exothermic process. So heat would be absorbed from the surroundings in an endothermic, sorry, that one's wrong, I don't know why I circled it, in an exothermic process, and so this one is also incorrect. So choice C is the only one that would be true about an exothermic reaction. The rest of them are all sort of stating the opposite of what would be true about exothermic. All right, so any questions on this problem or those concepts dealing with exothermic and endothermic reactions? Yep?
So the bond energy in an exothermic reaction is greater on the products than the reactants?
Yes, and that comes a little bit, you can see it from this relationship here. Remember, we're gonna do a problem exactly like this later, where you take bond energies of reactants minus bond energy of the products. If you're getting a negative number out, that means this value is larger than this value. So mathematically, you can think about it that way too. And conceptually, again, as we said, it's because when you form bonds, you release energy. So you have to release more energy in the bonds that you form than you take in the bonds you break, and that will give you overall an exothermic process that releases heat to the surroundings. All right, other questions?
So for E to be correct, will be the reaction release heat?
Yeah, and that's sort of related to choice C here. So the reason the temperature of the surroundings increases is because the reaction is releasing heat to the surroundings. So if it was releasing heat, then it would be correct for choice C. Yeah. All right, anything else? All right, we're going to go on then to number 4 here. So number 4 deals with what's called a thermochemical equation. A thermochemical equation is a balanced chemical equation with its associated delta H value. This would be a combustion equation, more specifically. So we want to know what the enthalpy change is in kilojoules when 12.5 liters of C2H6, which is called ethane, measured at 25 degrees Celsius to 780 torr, is burned in air. And so we want to give the answer with 1 decimal place and no units. All right, so this is kind of an involved problem which actually combines concepts from Chapter 7 and Chapter 8. And I don't know that there will be a problem on the exam that does this exact thing, but it is helpful because it combines two things that you will need to be tested on next week. And so the first aspect of this is when you're talking about a thermochemical equation, what we're trying to find here is what is the enthalpy change, or the heat of the reaction is another way of saying that, when we're burning this much of our reactant C2H6. And the amount of reactant that we're giving to you could be in terms of grams is probably the most common, but it could be in terms of moles. But in this case, it's a gas, and we're giving it to you in terms of its volume, temperature, and pressure. So in a problem like this, you're going to treat it a lot like a stoichiometry problem. We're going to figure out how much substance are we reacting, in this case, how much are we burning in a combustion reaction, and if we burn that much substance, how much heat, how much delta H are we going to have when we burn that amount? And so you're going to treat it like a stoichiometry problem, and just like any stoichiometry problem, the first thing you should think about is how do we figure out how many moles of substance we're burning? And there's different ways to do that depending on what kind of reaction it is, as we talked about in chapters 5 and 6, and now in chapter 8, which is the gas law chapter, we learned another way to relate moles of substance to other quantities. So because this is a gas and because we have volume, temperature, and pressure, we should immediately think of the ideal gas equation. So for that reactant, all these are gases in this equation, but for the reactant C2H6, which is what we're talking about here, we can use the ideal gas equation, and we can solve for the number of moles as pressure times volume divided by RT. So in a gas stoichiometry problem, this is sort of like a gas stoichiometry problem combined with a thermochemical equation, sort of two things in one here. But you can find moles of substance for a gas using the ideal gas equation like we do here. Now for this to work, we're using R in the calculation. R has specific units of liter atmospheres per k mole, so that means pressure needs to be in atmospheres for this to work. Volume in liters, which it already is. So we'll have to do that conversion again that we did in the first problem, converting torr to atmosphere. So the pressure of our reactant is 780 torr, so we just have to divide by 760 to get it into atmospheres. So it's not all that different than 1 atmosphere, it's 1.03. All right, so that's the pressure in the correct units, and then we can now calculate the moles of that substance, C2H6, using PV over RT. So the pressure is 1.03 atmospheres. Volume is given to us as 12.5 liters. And then RT in the denominator. R is the universal gas constant. It's on the periodic table if you forget it, but it's a number that we'll use a lot throughout this exam. So it's going to be liter atmospheres per k mole. And then the temperature has to be in Kelvin. So the temperature is 25 Celsius. We add 273 to that. to get it to Kelvin should be 298. So anytime you're doing problems where you have absolute temperature, just T, not delta T, absolute temperature needs to be in Kelvin for any problem involving ideal gases or other equations where it's just temperature. So we're going to use Kelvin for that, and we're going to get 0.526 moles of C2H6. So that's how much substance we're burning in moles, and then we're going to set it up like a stoichiometry problem to figure out what is the enthalpy change when this much of the substance burns. So we're looking for the enthalpy change, heat of reaction, or we can abbreviate it as delta H. We have 0.526 moles of C2H6. And then, as I said, we're going to treat this thermochemical equation just like would any other equation, where we're going to use the given delta H as sort of another product of this reaction. So when 2 moles of C2H6 burns, we're going to have an enthalpy change of minus 2,855 kilojoules. That delta H is associated directly with the coefficients in the equation. So it's going to be per 2 moles of C2H6 because there's a coefficient of 2 there. So the conversion that we're going to do then is we're going to have, we want moles of C2H6 to cancel out. And we figure out how much kilojoules of enthalpy change do we have. So we're going to put the enthalpy change on the top. And again, that's per 2 moles of C2H6 because of the coefficient of 2 that's given in the balanced equation. So then numerically that comes out to minus 750.9 kilojoules. In a Blackboard problem, you would just enter in the number, of course, not the units, but that's the correct number in kilojoules as we specify. All right, so any questions on number 4 or the process of using thermochemical equations to, in this case, calculate delta H? We could also go in the opposite direction where we give you an enthalpy change and figure out how much substance is needed to produce that. That would be, in this case, starting with a given delta H and moving backwards using this in the opposite direction, but nonetheless, it's the same concept and it's very much related to stoichiometry. So anything you want to rehash on that topic? Yep.
Will there be like a question that involves limiting reactants?
Possibly. So if you're doing a problem like this, where we gave you amounts of both of the reactants, C2H6 and O2 or whatever they are, then you need to figure out the limiting reactant first before you can figure out the enthalpy change. Because just like the limiting reactant is going to limit how much product forms, it's also going to limit how much heat change you have or how much enthalpy change you have in that reaction. So anytime you see amounts for both reactants, you should automatically think that you need to find limiting reactant first, but then from there, the steps would be the same as I outlined here. All right, other questions?
So like delta H is heat of formation.
It's not formation in this case. So if it's delta HF, that would be formation, but that's a specific type of chemical equation that involves forming a compound from its elements. This is just a delta H for a reaction.
So like the degree thing.
So the degree is, we didn't really talk about exactly what that means. That'll come up more in Chem 2, but that tells you that it's measured at standard conditions, which means 25 degrees Celsius and some things about, I think, 1 atmosphere of pressure and stuff like that. So it for our purposes, you don't have to really worry about what that circle means. We're just going to use the numbers as they're given to us. Okay. All right, on number 5 then. Doing okay on time. All right, so number 5, we have a 5-gram copper slug. That just means it's not an animal, it's just a piece of metal. And it's heated to a temperature of 100 degrees Celsius. It's placed into a cup of 10 milliliters of water, initially at 23 degrees Celsius. What is the final temperature in Celsius, assuming no heat is lost? And then enter your answer with 2 decimal places. So in a problem like this, where we're putting 2 substances together, one of them at a higher temperature, one of them at a lower temperature, there's going to be heat transfer between those 2 things. And essentially the heat change for one substance is equal to the negative of the heat, the heat for one substance is equal to the negative of the heat for the other. So they're going to transfer an equal amount of heat between each other, but one of them is going to be losing heat, one of them is going to be gaining heat, so they're opposite in sign. So you have to remember to put a minus sign on one side of this to make sure that you're getting the math right. Now the other thing to keep in mind is sometimes if we're doing this in the calorimeter, the term on one side could have, the heat on one side could have 2 terms involved with it. We'll see this in the next problem as well, where it could be the water that's in the calorimeter, and then also you have to maybe consider the calorimeter itself as absorbing some of the heat. So you might have to account for this sometimes as well. In this problem, it doesn't matter because we're not telling you anything about the heat capacity of the calorimeter. We're telling you to assume that no heat is lost. So what we're assuming in this problem is just that we have this simple situation here. Whatever heat is lost by the copper, which is initially at the higher temperature, is going to be absorbed by the water. And so it's just those two terms that you need. And so for each substance then, the heat is going to be equal to mc delta T. All right, and so what we have then is this relationship here. The mass of the copper times its heat capacity times its delta T is going to be equal and opposite to that for water. Mass of water, heat capacity of water, delta T for water. And in these problems, what we're solving for here is final temperature, and we have to recognize that delta T for both substances is equal to, again, delta always means final minus initial. So it's final temperature minus initial temperature, and we're going to solve for that as our unknown. So from here, it's just going to be an algebra problem. So we're going to start putting numbers in and find out where our unknowns are. So for copper, we have 5 grams as our mass. The heat capacity of copper is given to us as 0.385 joules per gram degree Celsius. And then the delta T we're going to write as final minus initial. So final temperature is going to be our unknown. And the initial temperature for copper is 100 degrees Celsius. That's what it originally was at before we mixed them together. And that's going to be equal, again, to the negative of the mass of the water. So for water, we have 10 milliliters. The density of water is 1. So the number of grams and number of milliliters is the same for water when you have density of 1. So that's just going to be written as 10 grams. Heat capacity of water is not given. It's the one heat capacity you should know. Again, I think we usually or maybe always provide it on the exam, but just to be safe, it's good to know it. If you do enough practice problems, you'll learn it because you're going to use it a lot. So it's 4.18 joules per gram degree Celsius. And then finally, we have the delta T term for water. So both substances are going to go to the same final temperature. That's when the heat transfer stops, is when they get to that final stable temperature. But then the initial temperature for water is different. The initial temperature for water was 23. All right, so 23 Celsius there. So that's what we're going to solve, and we have to solve for our unknown TF. The algebra for this is not trivial, but it's not too bad either. So I'm not going to go through all the steps, but you'll do the algebra and find that your final temperature is 26.39. They wanted 2 decimal places here, so that's how we'll report it, and that would be in degrees Celsius. Your final temperature should be in between the two. So copper was at 100, the water was at 23. Your final temperature needs to fall somewhere in between those two. If it's not, that means you messed up something. But again, the key step that most people forget in problems like this is putting a minus sign on one side of the equation. It can go on either side. It doesn't matter if it's here or here, but it needs to be in one of those two places. And you don't want to change the order of the temperatures. It's always final minus initial for both sides. You just need to make sure that you're putting a negative sign out front, the equation here or here, wherever you prefer to put it. All right, so any questions on that one? Yep.
So the temperature does not have to be changed to Kelvin.
For these ones, no. So anytime you have delta T, you're talking about a difference between two temperatures. It would be the same whether it's Celsius or Kelvin. So if we had changed both of these to Kelvin, so for example, the for water, delta T, now that we have the final temperature, is 26.39 minus 23.0, which is 3.39 degrees Celsius. If we did it in Kelvin, the final temperature in Kelvin would be 299.39, and the initial temperature would be 296, and that would still be a difference of 3.39. So numerically, they're the same, whether you're talking about delta T in temperature in Celsius or Kelvin. In this problem, we specifically wanted the final temperature in degrees Celsius, so that's why I just left everything in that unit and didn't convert it. So you wouldn't be wrong if you converted it, but then you have to make sure that you report the final temperature in the correct unit, which for this one would be Celsius. But you don't have to change it because it's a delta T. Yep.
And we can put a negative on either side.
Yeah, so the minus sign could be here or here. It'll mathematically work the same.
And when are you going to use that one? The one with that?
So these ones here.
Yeah.
So in some problems, including the next one that we're going to do, I believe, which is a chemical reaction, a calorimeter. But in some calorimetry problems where the two major variations are something like this, where you're just studying heat transfer between two substances and either calculating a heat capacity or a delta T or something like we did here, or a chemical reaction. Those are the two major types. The calorimeter is going to technically have two terms associated with it. So this is going to be the amount of heat that's absorbed by the water. This is going to be the amount of heat that's absorbed by the calorimeter itself. Now, depending on what information we give you, sometimes we'll use both of those two terms explicitly, or sometimes we'll just kind of group it all together into one. So you just have to look at what information is in the problem to guide you. So in this problem here, we didn't tell you, when we told you it's placed in a cup, so we know that our calorimeter is made out of a cup of some sort, but we don't tell you the heat capacity of the calorimeter itself, so we can't account for it. We're assuming that all of the heat is absorbed by the water, and that the heat absorbed by the cup is negligible. So it's going to come down, it's always this, but one or both of the terms will be used depending on the information that you have. And then sometimes what we do is we just group both of them together into one, which would just look more like this, just one term with a heat capacity and a delta T, not a specific heat capacity. But it again comes down to how the problem is set up and what information we give you. All right, anything else? Yeah?
So for the mass of water, so the milliliters just equals the gram?
For water specifically, yes, because the density of water is 1 gram per milliliter. So in this problem, the grams of water, we have 10 milliliters, and if we do a conversion, it's just 1 gram per milliliter, so it's just the same number. So for water, you can just do that. You don't have to necessarily write it out like that. It's just a trivial conversion. And in problems involving calorimetry, water would be, likely the liquid that's in there anyway, so you don't have to worry about other things coming into play. All right, anything else? All right, the next one here deals with another calorimetry problem. And this is one where the questions that came up in the last one will be more important. So here we have the heat capacity for a calorimeter by itself is this number here. So we're giving you the heat capacity of the calorimeter, which we didn't tell you last time, and it's filled with 1 liter of water. So we also know how much water is in there. So in this problem, we're going to have to use both terms, as we'll see. We're burning a 5-gram sample of acetic acid, and it raises the temperature by 5.4 degrees Celsius. Use this information to determine the enthalpy change in kilojoules per mole for the combustion of acetic acid, as shown below. And okay, so in problems like this is a pretty standard calorimetry problem where you're going to follow 3 steps to get to your final answer. Now, in some problems, you have to be aware that you might have to do these 3 steps in different orders, because sometimes the unknown is not the delta H that we're looking for, but it could be the heat capacity, which is not given, or the delta T like we did in the last problem. So keep in mind that sometimes these 3 steps might be done in different orders, but it's always going to be the same 3 steps that are involved. The first and third involve a little bit of math. The second one is pretty trivial, as we'll see. So the first thing we're going to do is going to be, again, the heat for the calorimeter, as we said in the last one, is going to be the heat that's absorbed by water, which is MC delta T for the water, and then the heat capacity of the calorimeter itself times delta T. And which of these terms you use, one or both of them, depends on what you're given in the problem. And as I mentioned when I was reading this, in this case we have both things. We have the amount of water in the calorimeter, again stated as a volume, but we can get the mass from that very easily. And we have the heat capacity of the calorimeter itself. So we're going to use both of these terms in this problem. All right, so that's the heat for the calorimeter, and that's going to be the first step in a typical calorimetry problem like this. So we're going to put the numbers in. The mass of water, we have 1 liter, which is 1,000 milliliters, which is 1,000 grams. So we want mass to be in grams because our heat capacity is in grams. The heat capacity of water is given here, but we should know it again because it's one that we use all the time. And then the delta T, the temperature raises by 5.4 Celsius. That means delta T is a positive number. And again, for delta T, we don't have to convert it. We don't want to convert it here because delta T is the same whether it's Celsius or Kelvin. The change in temperature is the difference between two. And then in this problem here, we want the answer to be in kilojoules. So I'm going to do it, I hope I don't confuse anybody with this. I'm going to do it in one step here because before we add these two terms together, they need to be in the same unit. This term is in joules because our heat capacity is in joules. So let's divide it by 1,000 to convert it to kilojoules right away so that we don't have to do a separate step there. But again, this is MC delta T. This is just to convert it into kilojoules. And then the second term, which is the heat capacity of the calorimeter itself times delta T. So the heat capacity of the calorimeter is 9.25 kilojoules per Kelvin. For an overall heat capacity, we don't include a mass term. It's just all grouped together into one capital C heat capacity as we abbreviate it. So it's going to be that number times delta T for the calorimeter. Again, we can rewrite it as kilojoules per degree Celsius because it's in terms of delta T, so it can be in Celsius or Kelvin. It's already in kilojoules, so we're not going to have to do any further conversion. We just multiply it by the delta T. So that will give us both terms in kilojoules, and then we can add them together to find heat for the calorimeter is 72.5. So that's sort of step one, if we're going to sort of label it, in a typical calorimetry problem involving a chemical reaction. Step two is trivial, but it's to recognize that the heat of the reaction that we're studying is just equal and opposite to the heat for the calorimeter. And again, that's because of the same concept we talked about in the last slide. When you're doing a process in a calorimeter, if the system, which is your chemical reaction in this case, is losing heat, that means the calorimeter is gaining heat and vice versa. So those two terms are the same in magnitude but opposite in sign. So if this is the heat for the calorimeter, positive 72.5 because of our positive delta T, that means the heat for the reaction is just the negative of that. So that's a trivial second step. We have to make sure we remember it to get the sign correct whenever we're calculating a delta H in this way. And then finally, the last step here is to recognize that what we're looking for is the delta H per mole of acetic acid, per mole of the substance here. Okay, so this is the delta H when we burn 5 grams of it, but we're not interested in that. We're interested in the delta H for this reaction here, which is per mole, 1 mole of CH3COOH. There's a coefficient of 1 there. So the last step is to take the heat of reaction and divide it by amount of substance, usually the moles, because most often delta H is reported per mole. All right, so we're going to divide the heat for the reaction by the moles of substance that we use. So it's going to be minus 72.5 kilojoules. Then we have to find the moles of acetic acid, which is 5 grams. And the molar mass for acetic acid was given to us as 60.02 up here. So we don't have to calculate it. So 0.0833 mole is the amount of substance that we burn. So if we divide the delta H, or the heat of the reaction, by that number, that'll give us the delta H per mole of substance, kilojoules per mole. And so that comes out to minus 870.3. This would be another numerical problem, so we would just enter the number into Blackboard without the units, but that would be in kilojoules. All right, so that's the amount of heat, delta H, for 1 mole of acetic acid. We measure the amount of heat for the reaction, which is 5 grams, divide that by the corresponding amount in moles, and that gives us the value there. So those are the 3 steps that you would go through in a typical calorimetry problem where you're measuring a delta H value or a delta E value for a reaction. But it's these 3 steps, sometimes in different orders, sometimes with different unknowns, but that's going to be the sort of unifying concept for all of them. All right, any questions on that? Why this step here?
Yeah.
So when you do a reaction in a calorimeter, so anytime we're measuring heat transfer, it's going to be, something's going to be defined as the system, something's going to be defined as the surroundings. There's going to be heat transfer between system and surroundings. In a calorimeter, the calorimeter itself is the surroundings. And so whatever the heat term is, in this case we're going to calculate heat for the surroundings first, the calorimeter, and then the heat for the system would just be the negative of that, because if the surroundings is gaining heat, it's positive, that means the system is losing heat, which is negative. So they have to be opposite in sign. And that's because what we're actually calculating here is for the surroundings, but what we're interested in is the heat of the system, which is our reaction. So they have to be negative. All right, other questions? Yeah?
Is the system always going to be a reaction?
Yeah, I mean, I'm not sure why you would define the system as the instrument you're using to measure the reaction. So yeah, if you're talking about a chemical reaction in a calorimeter, that would always be your system. And most of the time we're going to be talking about combustion reactions, which you should have a negative delta H anyway, even if you're sort of forget about this step, recognize that combustion reactions are exothermic. So make sure your answer is negative at the end if that's the type of reaction you're talking about. All right, anything else?
Why do you have to divide by the mole?
Because in this here, what we're looking for is we're looking for the enthalpy change in kilojoules per mole for the combustion of acetic acid. So the combustion of acetic acid is written with a coefficient of 1 in front of it. So if we want to find the delta H for this reaction, that's going to involve 1 mole of CH3COH. In the calorimeter, we only burn 5 grams. So the initial heat of reaction we get is not per 1 mole, it's per 0.0833 moles. So dividing the two allows us to figure out what would delta H be if we were burning 1 mole of that substance, which is what we're looking for. Great. All right, number 7 here is what's called a Hess's law problem. This is where we're going to give you 2 or more thermochemical equations, and we're going to ask you to combine them in some ways to find the delta H for some other reaction. So in this problem here, we're looking for the delta H of formation for B2H6 using the data given down here with 3 different equations. Now, in a lot of problems like this, we will explicitly tell you which chemical equation you want to find delta H for. And here we're not actually giving you that. We're telling you to find delta H of formation. But remember that whenever we see this little F there for formation, that refers to a specific type of chemical equation. So if they're talking about the delta H of formation for B2H6, it's going to be the enthalpy change when we form that substance from the elements in their standard states. So the equation that we're going to write that's going to correspond to this delta H that we're looking for is the formation of this compound from elements. So boron in its standard state is just B. So you'll need 2 borons to balance that out. And then the standard state for hydrogen, which is the other element that makes up this compound, is H2. It's one of the many diatomic nonmetal elements that we have. Most of the gas phase nonmetals like H2, O2, N2, and so on. And so we're going to have H2 as the other reactant, which needs a coefficient of 3 to be able to balance out both sides. And again, in a formation equation, you always want a coefficient of 1 on the product side. So you don't want any coefficients on the product side. So this would be the equation that corresponds to the delta H of formation. So the delta H for this reaction is equal to the delta H of formation of B2H6, because this is the chemical equation for the formation of B2H6 from its elements. So what we need to do then is we need to figure out how to combine these 3 equations to be able to get this overall equation here. And then once we combine those 3 equations, we can add the modified delta H values, and that will give us the delta H for this reaction. All right, so we're going to number these 1, 2, and 3 to keep them straight from each other. And if we look at this, our overall equation that we're trying to find delta H for, it has a coefficient of 2 in front of boron. This first equation has a coefficient of 4, so we're going to need to multiply this by 1/2. So we want to find the reactants and the products in this equation here that only appear once in the given equation. So boron B only appears in equation 1. It has a coefficient of 4 in that equation. It needs to be 2, so we're going to multiply equation 1 by 1/2. So this is kind of, again, like putting a puzzle together where you just have to figure out how to modify and combine these 3 equations to get this overall equation here. So if we have the first equation, we're going to take all the coefficients from equation 1 and multiply them by 1/2. I'll leave the solid gas things out. We don't really need those for this one. And so we're going to take all the coefficients from equation 1 and multiply them by 1/2. And that means the delta H for this, once we modify the coefficients, is also going to be 1/2 times the original value. So it's minus 2,509.1. We're going to divide that by 2, or halve it, to get the delta H for this modified equation here. So it'd be, to round it to 1 decimal place, minus 1254.6. All right, and then what we're going to find out is what we do with the other ones. So our overall equation we're trying to find delta H for has 3 H2s. H2 appears in equation 2, but with a coefficient of 2 and not 3. So what do we have to multiply equation 2 by to get this coefficient of 2 into coefficient of 3? Any takers on that? 1.5 or 3/2. So I heard a 1.5, so that's correct. I'll put it in as 3/2, the same thing. So we're going to do 3/2 times equation 2, which is going to multiply all of these coefficients by 3/2. So you're going to get 3H2 again 3/2 O2, and then 2 again times 3/2 is 3 H2Os. All right, delta H for this, because we multiply by 3/2, is going to be 3/2 times the delta H for that original equation 2 there. So that number times 3/2 is minus 857.6. All right, and then the last one here, we want one B2H6 as a product, but B2H6 shows up in the third equation as a reactant. So if it's on the wrong side of the arrow, we just need to flip the whole thing, and that's equivalent to flipping the sign of the delta H for that. So we're going to take the negative of equation 3, which is equivalent to flipping it. So the reactants in equation 3 become the products, and the products in equation 3 become the reactants. So B2O3 and 3H2Os go over onto the left side. And then on the product side, we have what was originally the two reactants, B2H6 and 3O2s. And so the delta H for this, because we flipped it, is just going to be the negative of the original delta H value. So the original delta H is negative 2,147.5, so we just take the minus sign off after we flip the direction. Okay, so those are going to be the three modified equations. If we trusted ourselves, at this point all we have to do to get the answer is just add together the three modified delta H values. We can check that the equations add up correctly, since that's always good to do if you have time. So on the reactant side, everything on the left side of the arrow is going to add together. Everything on the right side of the arrow is going to add together. Things that appear on both sides will cancel out. So we have two borons that carry through. We have 3/2 O2 here. We have another 3/2 O2 there. So on the left side of the arrow, we have 3 O2s from those two equations. Then we have 3 O2 there on the right side. So those all cancel out because there's 3 O2s on both sides of the arrow. We have 3 H2s, which doesn't cancel out with anything. And then here we have B2O3 as a reactant in equation 3 after we modified it, which cancels out with that B2O3 that's a product in that one. And then our 3H2O, we have 3H2O as a reactant here, but they cancel out with the 3H2O on the other side of the arrow from that second equation. So everything else cancels out, and all that we're left with on the product side is B2H6. So those three add together correctly to give the equation we're looking for, and now we can just add the three delta H values. So the delta H for this reaction, which is the delta H of formation for B2H6, is those three numbers added together, minus 1254.6 minus 857.6, and then 2147.5. So those three added together, it comes out to 35.3 kilojoules, positive number. And that would be choice B here. Okay, so in problems like this, if we're giving you 2 or 3 equations, the approach you're going to typically want to take is figure out how to combine those 2 or 3 equations to generate the chemical equation that you're trying to find the delta H of. In this case, we didn't give you that directly. You had to produce it yourself, knowing the definition of a formation equation. Okay, so any questions on that? All right. And then the other way that we could ask you to calculate delta H for a reaction where we're not, there's calorimetry, which is sort of an experimental way of doing it, and then there's these two methods, or 2 or 3 methods, I suppose, for calculating it. So this one here is really the same concept, but in this problem here, we're not giving you chemical equations, we're just giving you a bunch of delta H values. But here's the information we're given. So we're looking for another formation, the enthalpy of formation for NH3, and we're giving you delta H of formation for NO2 and H2O, and we're giving you this equation here along with its delta H value. So in problems like this, if you wanted to, you could write out all of the formation equations and then try to figure out how to add them all up to get the overall equation and find what's the unknown. But that's going to be a little bit unwieldy here because it's, you have to produce a few equations, you have to figure out how to combine them, you have to find your unknown delta H that way. So that's not going to be the most straightforward way to do this. The most straightforward way to do this is to realize that if all of the given enthalpy values are formation, so we're giving you 2 delta H's formation, we're asking you to find a delta H of formation, we have to remember that the delta H for a reaction can be calculated as the sum of the delta H's of formation for products, where M is the coefficients on the product side, minus the sum of the delta H's of formation for reactants. So in problems like this, where everything that you're given is a formation equation, and then we have one overall equation here with the delta H associated with it, this is going to be how we would set it up. We don't need to write out all the equations. We can just trust that it'll work out this way, because whenever we have formation equations specifically, this will always work out. All right, so then what we're going to do in this problem is we just need to figure out what our unknown is. So we have the delta H for the reaction. That's this number here. We have the delta H's of formation of both products, NO2 and H2O. So the only unknowns are going to be the delta H of formation for NH3, which is what we're looking for, and the delta H of formation of O2. Now, what is the delta H of formation for O2? 0. Why?
Because it's in its normal state.
Yep, it's an element in its standard state. So any pure element in its standard state, O2 being a classic example that shows up a lot, would have an delta H formation of 0. So we don't actually need that number to solve this equation, because it's just 0. So putting the numbers in, the delta H for our reaction is minus 1134.4 kilojoules, and that's going to be equal to the sum of the products minus reactants. So on the product side, we have 4 NO2s, so we're going to take 4 times its delta H formation, technically 4 moles, because there's 4 moles of product, and then delta H of formation for that product is 33.2 kilojoules per mole. And then for the other product, which is water, we have a coefficient of 6, so there's going to be 6 moles of water, and the delta H of formation for H2O gas is minus 241.8. And then we're going to subtract from that the sum of the delta H's of formation for the reactants. So on the reactant side, we have 4 NH3s. That has a delta H formation that we're trying to solve for. And as we said, oxygen is 0, so it's just going to be 7 times 0. So that one just, again, goes to 0. We don't really need to worry about it. So in this problem here, we have only one unknown, which is the delta H of formation for NH3. So I'm not going to go through the details of the algebra, but just move everything over and solve. And you'll get minus 45.9 kilojoules per mole. It should be kilojoules per mole. These should be per mole values, but don't get too concerned about the units. That would be the answer that you would pick there, minus 45.9 kilojoules per mole, technically. Okay, so again, this equation here is going to be useful either for finding delta H for a reaction, if you know the delta H of formation of all the products and reactants, or in this case, there was one we didn't know, but we could use it to solve for that one unknown, and it works the same way. All right, any questions on that? Yeah, go ahead.
So any element of the pure state will be 0?
Yeah, delta H of formation for any element in its standard state. So you have to know a little bit about what the standard states are. For pretty much all metals, it's just going to be the metal by itself. But for a lot of the non-metals, they are polyatomic. So there's, H2, N2, O2, F2, Cl2, Br2, I2, and then there's P4, S8. Those are the ones that are not just single atoms, but are polyatomic. But those are all considered standard states, and they would all have delta H of formation of 0.
But NH3, it's not a plus.
It's not an ion, but it's a molecule. So anything that has 2 different elements in it, N and H, is not an element, it's a compound. And so those compounds will, I suppose by coincidence they could have delta H formation of 0, but in reality they're all going to be non-zero because it's forming a compound from elements, so there'll be some enthalpy change associated with that. Yep.
So would you say like the way that the wording of the problem is, so the last one it was like you listed the formulas, is that like, if we look at it and like, oh, they're listing the formulas, we would use the different H's?
Yeah, so the reason we can't just do products minus reactants here is because these are not all formation equations. Actually, these first 2 are, sort of. This one's sort of double the formation equation because of the coefficient of 2 there. But this third one here is not a formation equation either, so we don't want to try to use any shortcuts for this one. We're going to just write out the equations and try to add them up. In this problem here, we're not giving you a bunch of thermochemical equations, we're just giving you a bunch of delta H formation values. So that should immediately clue you in to think about using this equation here, which is simpler because then we don't have to write out all the equations, we just have to know the numbers for each of those delta H formation, and that'll get us to where we need to go. All right, anything else?
And for bond energies, it will be the opposite, right? It will be like reactants minus.
Yeah, we're going to do that here in a second, right here. So you jumped the gun, but here we are. All right, so we're going to do a problem now where we're going to use bond energies, or bond strengths as they're often called, to estimate the delta E. It could be delta H also. They're kind of mean the same thing as we talked about in kilojoules. So again, it's a numerical problem. So in problems like this, what you have to do is, it's a little bit more complicated because you have to keep in mind every single individual bond that's on the reactants and product side, not just each molecule or each substance, but each individual bond that's present. So you do have to draw Lewis structures for these to make sure you're getting the right bond orders in some cases. Some of them are obvious and easy, some of them you have to make sure you get. So if we drew Lewis structures really quick for these, so in COCl2, remember that carbon should have a complete octet with 4 bonds. The lone pairs are not really important, but I'll draw them in for completeness. But you have to recognize that in COCl2, it's a carbon-oxygen double bond, because you need that double bond there to complete the octet on carbon. Otherwise, it would only have 6 valence electrons. In this problem, we gave you bond orders for carbon-oxygen that are both triple, double, and single, so we have to make sure we're using the right one, because all those numbers are different. So that's the correct structure of that. Water, of course, is easy. It's just 2 OH bonds. And then on the product side, we have CO2. Again, by virtue of the octet rule, those need to be double bonds to complete the octets on both carbon and oxygen in this case. And then finally, HCl is a pretty easy one. It's just hydrogen bonded to chlorine, but it has a coefficient of 2, so you have to recognize that on the product side, there's 2 HCl bonds, even though each molecule only has 1. All right, so then what we're going to do is we're going to sum up all the bonds on the reactants and product side and just subtract them from each other. So on the reactant side, in whatever order we do this in, that doesn't really matter, but our first reactant here has 1 CO double bond. And again, we gave you bond energies for triple, double, and single, so you have to make sure you're using the correct one. So it's a CO double bond, so we're going to use that number there, which is 745. In problems like this, and in other problems that are going to be possible on this exam, you don't necessarily need to use all the numbers, so don't forget if you don't use all of them, they might not be used. So we're going to use that one for C double bond O. And then this reactant here has, this is called phosgene. This is really nasty stuff, by the way. But anyway, it has 2 carbon-chlorine bonds, CCl, CCl. So that's going to be 2 times that value there for carbon-chlorine, 339. So that's 678. And then we have, in water, 2 OH bonds. So it's 1 water molecule, but it has 2 bonds. So we're going to count both of those individually. And that's going to be 2 times 467, which is 934. So the sum of those 3 numbers for the reactant side are 2,357 kilojoules. And then on the product side, we have to do the same thing. It's a little bit simpler on the product side. And what we have in the product side is we have 1 molecule of CO2, but it has 2 CO double bonds now. So we have to count both of those. So we have 2 CO double bonds. So we're going to use the same number as we did above, but it's going to be 2 times that number now. And then we have 2 HCl. So each HCl has 1 bond, but there's a coefficient of 2, so there's going to be a total of 2 bonds between hydrogen and chlorine. And the HCl bond strength is 427 from our list of bond energies. So it's going to be 2 times 427, which is 854. And then when we add those together, we get 2,344. All right, and then what's left is to calculate delta E or delta H, however it's stated. And again, we can estimate that as the sum of the bond energies of reactants minus products. So you have to remember that there's a switch here. For delta H formation that we did in the last problem, it was products minus reactants. For bond energies, it's reactants minus products. That's because bond energy is defined as the amount of energy needed to break a bond. So we're going to be breaking bonds on the reactant side. which is endothermic, forming bonds on the product side, which is exothermic. So that's why we're going to take those and subtract them in that way. Reactants minus products. So the first number was 2,357 for the reactant side, 2,344 for product side. So this is not a very big enthalpy change, but it comes out to a positive number. It's going to be positive 13 kilojoules. All right, if you had switched those and done products minus reactants, of course you'd get the negative of that. This is another numerical problem, so you would just enter it as, it says 1 decimal place. Blackboard doesn't really care how many decimal places you put in. We just do that to make sure you're not rounding the number too much. So you put it in as 13.0, but even if you just put it in as 13, it'd be counted right. Okay, so that's going to be how we would set up a problem like that in terms of bond energy. You have to count all the individual bonds, and this time is reactants minus products. All right, any questions? All right.
So the delta H, they always have where you would switch your products and reactants?
Yeah, so there's two major ways of calculating delta H that look similar. So in this one here, if it's formation enthalpies, then it's products minus reactants. Here, if it's bond energies, it was, I think, originally introduced in the book as delta E, but again, this could be delta H as well. They're kind of used interchangeably. So you'd be calculating delta H, but when you're using bond energy, then it's reactants minus products, yeah. Okay, anything else? All right, we're on, so we've finished the chapter 7 material finally. So that's going to be, as you can tell, almost half of the exam. So make sure you're clear on chapter 7. Now we're moving on to gas laws. That's going to be what we would cover in chapter 8. It's going to be another major portion of this exam. So a balloon filled with an ideal gas has a volume of 253 milliliters at 24 degrees Celsius. What is the volume if the temperature is increased to 86 degrees Celsius? So in problems like this where you're changing something about a gas, so we have an initial volume and initial temperature. We're changing the temperature and we want to know what is the new volume. We have a bunch of relationships for that. This would technically be Charles's law because it's volume and temperature. But we don't have to remember every single equation. We can always start with PV equals nRT. And then we just move everything that's changing over to one side, everything that's constant to the other. So in this problem, as we said, volume and temperature are changing. So we're going to divide both sides by T, and then we're going to divide both sides by P to move pressure over. And so in this problem, we're not telling you explicitly that the pressure is constant, but if we don't tell you anything about it, you would just assume that it's constant. So these are all constants on this side of the equation. All right, so those are the two things that are changing, and when those are changing, you can write a relationship like this, where V1 over T1 equals V2 over T2. So that's going to be the ratio of those two parameters as they are changed by an ideal gas. So what we're solving for in this problem is V2, the final volume. So we can do it numerically or we can do it algebraically first, however you prefer to do that. So V2 would be V1 times T2 over T1, and then it just becomes a matter of plugging in the numbers. So the initial volume V1 is 253 milliliters. And then this is going to be T2 and this is going to be T1, but they have to be in Kelvin for problems where you're using absolute temperature. Even if it's a ratio of two temperatures, it has to be still in Kelvin. So T1 in Kelvin is going to be 24 Celsius plus 273, which is 297. And then T2, which is 86 degrees Celsius, we add 273 to that, and it comes out to 359 Kelvin. Okay, so we need to make sure that we're doing these in the correct units, and it has to be Kelvin for temperature in any gas law problem. So T2 is 359, and then T1 in the bottom is 297. So it's not a huge volume change, but it does increase because of the increase in temperature, and it comes out to 306 milliliters, which is going to be answer choice C in this multiple choice question. All right, so we can derive relationships involving any two or even any three of the different values, P, V, N, and T, using the same approach, and then we solve for whatever one we're looking for as our unknown. All right, questions on that?
So, whenever we're changing, like whenever we have to do the conversion process to change like pressure into atmospheres, if it's given in torrs or millimeters for mercury, when is it okay not to convert it?
So you have to do it in atmospheres if you're doing a calculation that involves R, because the value of R is specifically in liter atmospheres per kmol. In this problem here, we removed R as a constant, so you can use Well, here we're not even dealing with pressure either because it's also constant, so you don't have to worry about it. But in our volume units can be whatever they want to be because the ratio of the two temperatures, the units cancel out for temperature, and then whatever unit we use for volume will be the unit that we have in our final answer. So we could have converted it to liters, but that would give us an answer in liters that we have to convert back. All of our choices are in milliliters here. But if we're using R in the calculation, if we're solving for just one set of conditions where R is included, in that case it has to be atmospheres and it has to be liters. But otherwise, for volume and pressure, you can change the units whatever you want. Temperature is non-negotiable. That has to be in Kelvin in any of these types of problems. Good. Yeah.
So if nothing's said about it, then we just assume it's constant.
Yeah, I mean, you can't do anything with it. You don't have a number for it or anything about it. So yes, it'll be assumed to be constant. All right. All right, and then number 11 here is another sort of similar problem. So we have a steel tank is filled with 126 grams of nitrogen at 298 Kelvin, giving a pressure of 235 kilopascals. What will the new pressure be if 96 grams of nitrogen is added and the temperature cools to 273 Kelvin? All right, so in this problem here, it's a rigid steel tank, and we give you the hint that it's fixed volume, so that means the volume is constant. But everything else is going to be changing. So in PV equals nRT, we're trying to calculate the new pressure. So we're telling you the pressure is possibly changing, so we have to calculate what that is. And then we're adding gas to the cylinder. So we start with some amount of nitrogen, and we're adding more. So the number of moles is changing throughout this process. And we're changing the temperatures. Initially at 298 Kelvin, and it's cooled to 273, so it's also a changing temperature. So for this one, we have to derive a relationship involving pressure, number of moles, and temperature. 3 things instead of 2. So this is another variation that you can see for these types of problems where it's going to involve 3 and not just 2 of those variables. But again, it's the same process. So we want to move the 3 things that are changing over to one side. So it's going to be pressure divided by NT. Then the other 2 things get moved over to the other side. R over V, volume is constant, R is constant. And so again, this ratio, pressure divided by moles times temperature, is a constant value. So that means the initial and final conditions, the initial and final ratios of those will have to be equal to each other. All right, and in this problem here, what we're solving for is the final pressure, which we'll call P2. So looking at the information that's given, we have our initial temperature and our final temperature there. We have our initial pressure there. The only thing we weren't directly given is the number of moles that we have, so we're going to have to calculate that as well. But what we're looking for is P2, which is going to be P1 times N2 times T2, cross-multiplying, divided by N1 times T1. So we're just doing a little bit of algebra to find that. And now we can start plugging in the numbers as we get them. So the initial pressure, P1, is 235 kPa. And again, it doesn't really matter what unit we use for this because we're not putting R into this calculation. So we can use whatever pressure and whatever volume units we want. So we're going to put it in directly as kilopascals, which is what we're looking for our final answer also. But now we have to find the number of moles that involve N2 and N1. We don't have those directly. So N1 is the amount that's initially present, 126 grams of nitrogen. We'll convert that to moles using its molar mass of 28. So mass to mole conversions do come into play at times in ideal gas problems as well. So this is going to be N1, but then remember that N2 is the total number of moles that are present at the end. So we're adding 96 grams. So for N2, the final number of moles, lowercase n2, we're adding 96.0 grams. So N2 is not just going to be this number converted to moles, it's going to be this number converted to moles plus the original. It's always going to be the total amount of gas present, not the amount that you're adding during the process. When we're talking about N in this equation, is how much total gas there is before and after. So what we're going to do for the final number of moles N2 is we're going to take the initial amount that we have, 4.50, and then we're adding 96 grams to that. So the 96.0 grams has to be converted to moles as well. Same gas, so it's the same molar mass. And that's going to come out to 7.93 moles. So that's the total amount of gas we have present when we take the initial amount and add 96 more grams, converting it to moles appropriately. So then from there, we're going to put all the numbers in. So the final number of moles is 7.93. The final temperature is 273 Kelvin, already in Kelvin, so we don't have to convert it. And then in the bottom, we have the initial number of moles, which is 4.50. And the initial temperature, which was 298 Kelvin. So now it's just multiplying and dividing. We get 379.4. The units would be kilopascals. Again, Blackboard just enter the numbers, so it would be that number there, which is the correct pressure in kilopascals. The pressure does go up. We added more gas. We also cooled it down. Those kind of work against each other, but in that, we expect the pressure to be higher than what it started as. All right, any questions on that? Yep.
What would be the conversion factors for pascals to atmosphere?
So it's also that 1 to 1.3. So 1 atmosphere, that might be another conversion that comes up that I don't think I mentioned before. 1 to 1.3 kilopascals, which we don't need it here because we're just staying in that unit. But if you needed to convert it, it would be 1 to 1.3. All right, anything else? Okay. All right, on to number 12. So number 12 is a gas stoichiometry problem. We have NO and Cl2 reacting to form NOCl. And we're giving you volumes of each at STP. And we know how many liters of NOCl are formed. All right, so in problems like this, we have to start out with a balanced equation because it is stoichiometry. So NO plus Cl2 goes to NOCl. And then what we need to balance this out is a coefficient of, let's see, we have 2 Cl's, we're going to put a coefficient of 2 there. That means we have 2 nitrogens and 2 oxygens, so we need a coefficient of 2 there. So relatively simple equation, but it has to be balanced for this to work. And we would have to find limiting reagent, yes, because we have amounts of both reactants, 32.5 liters of NO, 21.2 liters of Cl2. Now, one thing I kind of glossed over in class, but we should be familiar with it now from the homework assignments, STP tells us that it's called standard temperature and pressure. So the temperature is 273 Kelvin, and the pressure is 1 atmosphere. So that's the temperature and pressure of this gas. And another relationship that's helpful for STP sometimes, we actually don't need it here as we'll see, but if you're at STP, 1 mole of any gas has a volume of 22.4 liters. So in gas stoichiometry problems, if you're more comfortable doing it this way, what you can always do is if you have the pressure, volume, and temperature, you can find number of moles using PV equals nRT. Because in a stoichiometry problem, as we introduced them starting in chapter 5, it revolves around moles of each substance in the reaction. Moles of reactants, moles of products, relationships between them. But we don't necessarily have to convert to moles in gas law problems if we're dealing with volumes, because from PV equals nRT, volume and number of moles are proportional to each other. So the relative number of moles of each substance that reacts is the same as the relative number of liters of each substance that reacts, whatever volume unit you choose. So when we read this equation here, again, conventionally it's read as 2 moles of NO reacts with 1 mole of Cl2 to form 2 moles of NOCl. But to save ourselves some time in problems like this, because we're dealing with liters of each reactant and we're trying to find liters of product that form, we can just read the coefficients in terms of volume as well when all the reactants and products are gases. Only when they're all gases, not any other situation. But 2 liters of NO reacts with 1 liter of Cl2 to form 2 liters of NOCl, and that's a perfectly valid way of reading that for a gas phase reaction because volume and number of moles are directly proportional. But however we choose to do it, whether we choose to use one of these conversions to find moles or we just work in volume, which is a little bit more straightforward in this case, we have to find the limiting reactant as, I'm sorry, I don't know her name, but as she said over here, sorry, what did you say it was? Alexis. So as Alexis pointed out at the very beginning of this, we need to find limiting reactant because we're telling you how much of each reactant we have. All right, so what we're going to do is for limiting reactant, the way that I introduced it in the past was to find a stoichiometric ratio for both. We did that before as moles divided by coefficient, but you can also, for a gas phase reaction, do it just as volume divided by coefficient, because again, those are directly related. So just working directly with volume, we have 32.5 liters of NO, and its coefficient is 2. So it's going to have a stoichiometric ratio of 16.25. And then for Cl2, using volumes to calculate stoichiometric ratio in this case, 21.2 liters. And the coefficient for Cl2 is 1. So it's just 21.2 divided by 1, which is 21.2. And just like any other stoichiometry problem, whichever of these is smaller is going to be the limiting reactant. So that means this one here. So NO is our limiting reactant. So when we're trying to figure out how much product forms, this is what we're going to start with, is the amount of NO that's present. So then it becomes a relatively simple stoichiometry problem where the liters of product NOCl that forms is the volume of our limiting reactant, NO, and then coefficients to find out the ratios of those that are involved. So we want liters of NO to cancel and liters of NOCl to be what we end up with. And again, we can read the coefficients directly as volume ratios for gas phase reactions. So 2 liters of NOCl will form for every 2 liters of NO that react. So that's going to give us then the same number, 32.5. And so we would just enter this number there, 32.5. So for gas phase reactions this work, we could have used this conversion or PV equals nRT to find number of moles of each and done it as a more traditional stoichiometry problem. But then at the end, we'd have to use PV equals nRT or this conversion again to go back into liters. So you'd basically just be doing steps and then undoing them at the end. So we can do it directly with liters if you're comfortable doing that. And it works out much faster and easier that way. But it'll give you the same answer either way, just less steps. Yep.
So if they weren't all gases, you can't like do this ratio thing?
Yeah, if they weren't all gases, then if you're trying to do if you're trying to do calculations that involve reactants or products that aren't gases, you'd have to go through moles in that case. So you should still be familiar with how to convert into moles using PV equals nRT or using this shortcut if you're at STP. And so in some cases you will have to do that depending on what you're asking to calculate, because those volume ratios only work if both things that you're considering are gases. But yeah, so you might have to do the other way as well. Yep.
Does the gas thing only have to, excuse me, does the whole equation need to be of gases or just the two things you're comparing?
No, I mean, if the two things you're comparing are gases, then you can still use that as well. I mean, in that case, it's not rigorously true because if you're, forming or consuming like a solid or a liquid, the volume will change during the reaction technically, but it's a close enough approximation that it would still work. But yeah, if it's all gases, it definitely works. But if you're just calculating two gases, you can still do that as well. It'd be fine.
So what's R? Is that stoichiometric?
Yeah, that's called stoichiometric ratio. So when you want to find out what the limiting reactant is, this is one way you can do it, the way that I taught in class, and you would take the amount of each substance, conventionally in moles, but in this case we can do it in terms of liters, and you divide by the coefficient. And whichever of those is smaller is identified then as the limiting reactant. All right, any other questions?
Like in this case, all of them are gases.
Yeah, they're all gases because we're saying that directly in the problem, but and this is why we can use that approach, yeah. All right, on to number 13. All right, so in this problem here, we have a 250 milliliter gas bulb filled with 0.379 grams of a gas at STP. Which of these is most likely to be the gas? And so again, we have this STP condition here. So we know that the pressure and the temperature right off the bat. Now in problems like this, when you're trying to identify an unknown gas, as we've done before in other types of problems, when you're identifying something that's unknown, you would try to find the molar mass of that and then compare it to the chemical formula and see which ones match up. So when you're doing problems with gases that involve finding the molar mass, either if we ask you to find the molar mass or we ask you to identify something based on its molar mass like we are here, there's sort of two ways to do it. Now the first way to do it would be to use the density equation. So we learned that you can rearrange the ideal gas law in terms of density, and it's pressure times molar mass divided by RT. So in a problem that specifically deals with density, this is a useful equation to have, and it involves the molar mass of the gas as part of it. Now in this problem though, we didn't specifically give you the density, although you could find it by dividing the mass by the volume in liters. This has to be in liters in this case because we're using R. Or the other way to do it is, and in general, when you're trying to find an unknown molar mass, is to remember that the definition of molar mass is the number of moles divided by, the grams divided by moles. So it's going to be the grams of the substance, in this case the unknown, whatever it is, divided by the moles of the unknown substance. So the definition of molar mass is the number of grams in 1 mole. And so if you can find the grams of the substance and the moles of the substance and divide the two, that's going to be another way to get the molar mass. So you can use the density equation and just solve for molar mass, but in this case you have to calculate density first because it's not directly given to you, but you have the mass and the volume, so you can do that. Or alternatively, we can just use ideal gas equation to find the moles of the substance, and then the grams is given, and we just divide the two to get molar mass. So both of these will work. Choose your favorite or learn both of them for different contexts. And I'll do the second one here just because in this case at STP especially, it's a little bit more straightforward. So grams is given to us directly. So that's 0.379. And we have to find the moles of the unknown using ideal gas equation. So we could again go to PV equals nRT, and we could solve for N, which is PV over RT. But again, at STP, don't abuse this relationship, but at STP, we also have the relationship that 22.4 liters is equivalent to 1 mole. So we can use that as a conversion factor as well for STP without going through all the steps like this. So again, a lot of different ways to approach this, but we'll do that shortcut to show you how it works. So if we want to find the moles of the unknown gas X, we have 250 milliliters of it. Capital X. And then we're going to convert to liters first, because this relationship involves liters. And then we're going to use this relationship here, 1 mole for every 22.4 liters. Shoot, I did this in my notes the other way, so now I don't have that number. Somebody can get some brownie points and help me, or I'll try to get it here in a second. Because I did this the other way in my notes, now I don't have this intermediate number here. We'll see who wins. Say it again.
0.011.
Can you give me one more decimal?
11.
111?
6.
6. 2?
1,
6?
1, 0.01116.
111. All right, that's enough. We'll do 1116. Okay, so that's how many moles of that gas we have. So we're going to put that back up here, 0.0, however many ones there are, and then a 6. And when we divide that out, we should get, I have the number here, let me make sure it works out the same. Yep, we get about 33.96. I got a slightly different number when I did it with density, but it's close enough. So 33.96 grams per mole is the molar mass of our unknown gas. And then we just have to figure out which of these gases here has a molar mass that's closest to that. So for pH3, we don't have to be too precise with this. The molar mass is 31 for phosphorus plus 3 hydrogens, so 34. That's really close. SO2 is going to be 64. Sulfur plus 2 oxygens. N2 is 28 grams per mole. Argon straight off the periodic table is 40. So the one that's closest is a pH3, which is called phosphine. So when you're identifying an unknown gas or trying to find molar mass of a gas, however the problem is stated, again, 2 ways to do it: density equation or just the general definition of molar mass, grams divided by moles, using ideal gas equation to find moles. And again, don't use this relationship here unless you're at STP, so I'm going to make sure that I warn you about that. Okay, so that relationship does not apply to all conditions, just STP when you have 1 atmosphere and 273 Kelvin for your temperature. Any other set of conditions, you can't use that shortcut, you'll have to use the full ideal gas equation, PV equals nRT, and put in the specific values for temperature and pressure that you have. Okay? All right, questions on that one? All right, on to number 14. So this problem here deals with mixing 2 gases together. So we have a tank with 3.25 grams of nitrogen with a volume of 9.3 liters. And then it's connected to a tank with 5.33 atmospheres of oxygen with a volume of 15.2 liters. So the valves separating the tanks is opened. What is the final pressure after the gases have mixed? No chemical reaction occurs and the temperature is constant. So whenever we're mixing two gases together, we should think about Dalton's law of partial pressures, which is that the total pressure in the mixture is equal to the pressure of each gas added together. So we have partial pressures for each gas in the mixture, in this case nitrogen and oxygen, and the sum of those two is going to be the total pressure. Now, the caveat here is you might think, oh, well, this is easy. I just have to add 3.25 and 5.33 and I'm done. But remember that these are the partial pressures after mixing, and when we mix the two gases together, the volumes are changing for each gas. So they're not going to have the same partial pressure before and after mixing. Because again, initially nitrogen occupies a volume of 9.3 liters, but after mixing together, it's going to occupy the entire volume of the two added together. So it's going to be, we have to do a little bit of work to get these two numbers. All right, so if you had just added those two numbers together, that would give you one of our answer choices, but it's not quite that simple because we have to find what these partial pressures are after the mixing process occurs, not beforehand. So for each gas, what we're going to do then is set up an ideal gas problem. So you have to do basically the ideal gas equation twice, and then once we get pressures of both gases, we'll add them at the end. So we're going to do PV equals nRT for each gas, and for these two gases here, pressure and volume are changing because initially they occupy their individual volumes. Once we mix them together, they're going to occupy the total combined volume of the containers. So imagine you just have two containers here, 9.3 and 15.2. And then once you open up the valve between them, they mix together, the gases will occupy that entire space. So the volume is changing for each gas after you mix it, and then the pressure, of course, would change as well. We're saying that the temperature is constant, and we're not changing the amount of gas that we have for each one, so it's going to be just a Boyle's law problem. So pressure times volume is equal to nRT. nRT are constant in this case, so it's going to be Boyle's law, P1V1 equals P2V2. So for each gas, we're going to do this type of problem. We're going to solve for P2, the final pressure of each gas after the mixing, which is the initial pressure of that gas, the initial volume of that gas, divided by the final volume, the total volume after mixing. All right, so for these problems here, V2, the final volume, is again the sum of the two volumes of the containers that the gases were originally in, because we're allowing the gases to mix in that total combined volume. So V2 is the sum of those two, 9.3 liters for the first tank, 15.2 liters for the second tank, which is 24.5 liters. So that's going to be V2 for both gases. So then we just have to solve for their final pressure. So for nitrogen, P2 is going to be P1V1 over V2. The initial pressure for nitrogen is 3.25 atmospheres. The initial volume for nitrogen is 9.30 liters. That's given in the problem. And then again, the final volume after they mix together is the combined volume of 24.5 liters. So the partial pressure of nitrogen after mixing is 1.23 atmospheres. It's lower because the volume has changed considerably. And then for O2, we do the same thing. Its partial pressure after mixing is its initial pressure and volume, which are 5.33 for the pressure, 15.2 for the volume, and then the same final volume for both, 24.5 liters. So for O2, its final partial pressure is 3.31 atmospheres. And so now what we can do is we have both partial pressures after mixing. We just add them together to get the total pressure after mixing. 1.23 atmospheres for nitrogen, 3.31 for oxygen, and the sum is 4.54 atmospheres. And that would be answer choice D for this problem here. All right, so for problems that involve mixing two gases together, if you want to find the total pressure, you need to somehow find either the partial pressures of each gas, which we could easily do here, or alternatively, you need to find the total number of moles of gas and then use PV equals nRT and solve for total pressure that way. So sometimes there's multiple ways we can do this, but in this problem here, we didn't tell you what the temperature was, so you don't have enough information to solve for the number of moles, and so we're going to just do it in terms of partial pressure. But we have to use Boyle's law for both gases to figure out what their partial pressure is after the mixing process occurs, and then we do that addition as the last step. All right, any questions on that? Yep.
There's another equation that involves like the total pressure, but it includes like the x.
Yeah, so that's it's chi. You have to learn the Greek alphabet for this class, unfortunately. So anyway, you're right though. So there is an equation that looks a lot like that, which is that the pressure of any gas in a mixture, which I'll call A here, is the mole fraction of that gas times the total pressure. So again, if you have enough information to find the moles of each gas, then you can find the mole fraction, and then you can get the partial pressure for each one this way as well. So this would be another one that you do want to make sure you understand how to use it, when it's appropriate to use it, and what it means. And this is another thing that goes along with the same concept of Dalton's law of partial pressures. So that's going to be correct way to do this in some cases. Here we can't use it again because we don't have enough information to find moles. So we're not going to be able to use this form of the equation anyway, but it is useful for some problems. Okay, other questions? All right, 15. All right, so in this problem here, just to cue you in on what you can expect on the exam, there's going to be for the last part of chapter 8, which dealt with kinetic molecular theory, the idea that gas molecules are in constant motion, they're colliding with each other, colliding with the walls of the container, and then also real gases, the deviations from ideal gas behavior. There's going to be a mixture of conceptual questions, but there's also one type of numerical question that may come up. So you might not all get a problem like this, but there's a good chance that many of you will, which is a problem that deals with effusion or diffusion, the process of a gas either leaking out of an opening or a gas sort of traveling through another gas, moving through space. And so this would be the numerical type of problem that would come up in this part of the test potentially. Again, not for all of you. There could also be conceptual questions. The next question is more of a conceptual nature, so we'll see kind of both of that in this review. But here we're talking about effusion of nitrogen, and we're telling you that it takes 2 minutes to effuse. And then if a sample of an unknown gas under the same conditions takes 3.9 minutes to diffuse, I guess it should be effuse because we're talking about effusion here. Should be the same word. That's just a typo. But what is the molar mass of the gas? So that's what we're asking for here, is the molar mass of our unknown gas. Now for problems like this, there's two forms of the equation. So if we're telling you about the rate of effusion or diffusion, or how much gas is effusing, if we're talking about it in that context, and in that case, they're going to be inversely related to the molar masses. All right, but this is not the form of the equation we want to use in this problem, because here we're talking about how long it takes the gas to effuse or diffuse. So to remember which form of the equation is appropriate, it's helpful to think about things conceptually a little bit. So when we're talking about effusion or diffusion, it's related to how fast the gas is moving. So if it's moving faster, it's going to leak out faster, or it's going to travel through space faster. And at a given temperature, gases that are lighter are going to be moving faster, gases that are heavier are going to be moving slower. So if you're talking about the rate at which something effuses or diffuses, it's going to be inversely related to the molar mass, because the lighter the gas, the faster, meaning the higher rate, or the heavier the gas, meaning the larger molar mass, the slower the rate. So this is going to be the form of the equation you would use if we're talking about how fast something is effusing. But here we're talking about the amount of time that it takes, and in this case they're going to be directly related to each other. Because if something is moving slower, it's going to take a longer amount of time, meaning that the heavier gas would take longer time. Time and molar mass in that case are directly related by the square root. So this is the form of the equation we're going to want to use here. You could put either N2 or the unknown gas X in the numerator or denominator, it doesn't matter. But the key aspect is that on the other side of the equation, the square roots of the molar masses need to be in the same way. So if we have N2 in the numerator here, and we're talking about the time that it takes for N2 to effuse, then the molar mass of N2 will be in the numerator on the other side of the equation. Or we could flip both sides and have X on top on both sides, N2 on the bottom. Either way will work algebraically, but you have to make sure you're using the correct form of the equation. So with this correct form of the equation, then we just have to put in the numbers and solve. And so the time that it takes N2 to effuse is 2 minutes. The time that it takes our unknown is 3.9 minutes. And then we're going to solve for the unknown molar mass. So the molar mass of N2 is 28, 2 times 14 for nitrogen. And then our unknown in the bottom here. All right. So we just have to square both sides, cross multiply, divide a few steps algebraically to get there. Before we even do it numerically though, before we even solve this, we can think about if this gas takes longer to effuse, that means it's moving slower, that means it's heavier. So we should get a number that's bigger than 28. So we can immediately cross off those answer choices, and if we got one of those numbers, that would probably mean that we set up our equation wrong. Because if it takes longer for something to leak, that means it's moving slower, that means it's heavier. But anyway, once we get the number, I'm going to skip the algebra again just to save a little bit of time. What we get is that the molar mass for gas X is 106 grams per mole. And that's going to be choice B here. So it has to be something that's bigger than 28 because it's a slower moving gas, takes longer to leak out than nitrogen does. All right, questions on that topic. So this is the type of numerical question that's related to kinetic molecular theory. It's sort of two slight variations, but relatively simple in terms of the math that goes into it. Yep.
Oh, there are only two variations?
I mean, the other one would be if you're talking about how much, like the amount of stuff that leaks out, I guess it's the same as this. So if you talked about this much nitrogen leaked out in the same period of time, this much of our unknown leaked out, then it would be the same form of the equation as rate. So the amount, how fast they're leaking out is proportional to how much leaks out in a given time. And so in that case, it would be also this. It should be X over N2.
When you use the rate thing,
When would we use that?
yeah.
So if we tell you that, usually in those problems, either we'll give you an absolute rate of effusion, like we'll say, nitrogen is leaking at a rate of 2.0 milliliters per minute, and the unknown gas is leaking at a rate of 3.9 milliliters per minute. So it's a rate term in that case, amount per time. Or a lot of times it'll be a ratio of two. So we'll say that, the rate of effusion for nitrogen is 2 times faster than the rate of effusion for the unknown gas. And so in that case, you don't know the absolute numbers, you just know that the ratio of the two, nitrogen over the unknown, would be 2, or whatever the number is that we give you. So those are kind of the ways that those would be stated. And in that case, you want to use the equation where they're inversely related on opposite sides of the equation. All right. Okay, let's go on to the next one. And then this is, I think, the last question that deals with Chapter 8, ideal gases. Although here we're talking about, again, conceptual things. There might also be things for real gases involved. So we want to know which of the following statements is false. So in a mixture of two gases A and B, the total pressure depends only on the total moles of A and B, not their identity. So thinking about choice A here, this is something that we kind of mentioned in the context of Dalton's law of partial pressure when we have mixtures of gases. PV equals nRT, and it doesn't matter in this equation. Remember, R is a universal constant. It's not dependent on what gas you have. It's always the same value for any gas. So it doesn't matter what gases you have, it just depends on the total moles. So whether we have one gas or a mixture of gases, we can find the total pressure if we just know the total number of moles of gas. So that one is going to be true because when we're doing questions that involve mixtures of gases, if we know the total moles, we can find the total pressure using PV equals nRT. It doesn't matter that they're a mixture of gases. It doesn't matter what they are. It'll always be the same math involved. All right, for choice B here, this one deals with two different gases, helium and oxygen, and they're both at STP. So again, STP means 1 atmosphere, 273 Kelvin. And it says they have the same average kinetic energy. So when we're talking about kinetic energy of a gas, this has a very simple relationship. We're not going to really use the exact equation, but it's equal to 3/2 RT. That's average kinetic energy for a gas, and it's just dependent on temperature. Again, it's not dependent on what gas it is. So when you're talking about the average kinetic energy, all that matters is temperature. Both of these gases are at STP. That means they're both at 273 Kelvin. That means they have the same average kinetic energy. So that one will be true as well. For kinetic energy, it only depends on temperature. But then for choice C here, we're dealing with the average molecular speeds of the gas. So we're comparing the same two gases, helium and oxygen, still at STP, but then it asks for, do they have the same or different molecular speeds with O2 being higher? So at a given temperature, we said they will have the same average kinetic energy, and that's going to be equal to 3/2 RT, as we said. But that's going to be also stated as 1/2 mass times velocity squared, average velocity squared. All right. So if the two gases have the same average kinetic energy, but if they have different masses, they have to have different velocities. That's the first thing. And then which one is larger and smaller? Well, if the mass is smaller, the velocity has to be bigger to give the same kinetic energy. And if the mass is bigger, the velocity will be smaller to give the same kinetic energy. That relates to what we talked about in the last problem, where if you have two gases at the same temperature, the heavier gas will be moving slower on average, the lighter gas will be moving faster. So in these two gases here, helium, which has a molar mass of 4, and oxygen, which has a molar mass of 32, the heavier gas should be moving slower. So the average speed for O2 should be lower than helium, not higher. So this statement would be false. So that could be one of our false statements, but we have to see also choice D, whether that one is going to be correct or not. So for O2 and helium at the same temperature, helium is smaller, lighter, so it should be moving faster, not slower than O2. And then finally for choice D here, deviations from the ideal gas law are smallest at high pressure and low temperature. So when we're talking about deviations from the ideal gas law, remember that they happen for two reasons. So deviations from the ideal gas law, so gases that follow PV equals nRT perfectly are called ideal gases. In real life, they don't follow this equation perfectly, and why is that? So the reasons are that, against related stuff we learned in chapter 9, real gas molecules have some attraction between each other. Those intermolecular forces, dispersion forces, dipole, whatever kind of forces are relevant. So real gas molecules are attracted to each other to some extent, and real gas molecules occupy some amount of volume. PV equals nRT assumes that the volume of the gas molecules itself is 0, and in reality that's not true. The gas molecules themselves occupy some of the space. And so those are the two reasons why you see deviations from PV equals nRT. So if you want to have the smallest deviations, what you need the gas molecules to be spread up as far apart as they can be, meaning you need to have a high, low pressure or high volume, putting them far apart from each other, or you need a high temperature. You need the gas molecules to be moving really fast so they don't have time to contact each other and have those forces of attraction. So choice D here is the exact opposite. So if we want to have smallest deviations from the ideal gas behavior, the conditions that we need are low pressure, large volume, small number of moles, and high temperature. These three deal with putting the gas molecules as far away from each other as possible so they don't interact and so they don't take up a lot of the space. And then the high temperature is because if the gas molecules are moving faster, they'll bounce off each other more fast and they won't stick together like they would in a real gas. So this one says that the deviations are smallest at high pressure and low temperature, which is the opposite of what's true. So that one is also a false statement. So we should pick choice E, which is that both of those C and D are false. So the smallest deviations occur under these conditions, where you're putting the gas molecules far apart and they're moving as fast as possible. All right, any questions on that? Any of these concepts related to kinetic molecular theory or real gases that kind of came up in this problem? Yep.
For the smallest deviations, it just has to be 2 or any of the two, or
Well, they're all kind of connected to each other. So because of PV equals nRT, if you have a low pressure, that typically means volume is relatively large, and then similar with that happens when you have, so they're all kind of related. So they won't always all be given to you, but it's some combination of these that would lead to the smallest deviations. Yeah. Yep.
Can you go over why the knockout speed for O2 is lower?
So it's lower because if they're at the same temperature, they have the same average kinetic energy. So if the kinetic energy is the same, but this mass can be thought of as the molar mass of each gas. And so for oxygen, it has a larger molar mass, so m is larger, which means velocity has to be smaller, because the product of these two, 1/2 mv squared, has to be the same for both gases. So if the mass is bigger, that means the velocity has to be smaller in order to have the same kinetic energy. So mathematically, that's how it works out. All right, other questions? All right, the last 4 problems, which is going to be accurate for how your exam goes, is going to be chapter 9 material, the most recent stuff we've covered. And just as a reminder, for we're starting chapter 9 now, but it's just going to be the first 4 sections of chapter 9. 9.1 to 9.4, phase diagrams being the last thing that's covered. So just as a reminder of what you should be responsible for. So these 4 questions will all deal with that stuff. It's going to be mostly intermolecular forces, liquids, phase changes, stuff like that. All right, so the first question here deals with intermolecular forces, and we want to know which forces are present in a sample of SF4. So to decide which intermolecular forces are present, we can look at the answer choice a little bit first. So the first one, A, everything has London dispersion forces. All right. So that's always going to be one of the intermolecular forces. Now, it's the weakest intermolecular force, so in many cases it's not the most important one if you have others. But everything has London dispersion forces. Doesn't matter what it is. Okay. So that's going to be one of our choices for this one, because no matter what the substance is, it has that. The second one, covalent bonds, is not going to be an intermolecular force. All right, covalent bonds refers to an intramolecular force, which is a force that holds atoms together in a single molecule. Remember, I'm getting those names mixed up. Intermolecular forces with ER, those are going to be forces that hold multiple molecules together. So the forces that cause two molecules to stick together in a liquid or a solid phase or whatever the case is. So this one's not even an intermolecular force, so it can't be our answer choice, but we have to decide, does this molecule have dipole-dipole forces or not? So the other intermolecular forces, dipole-dipole forces and hydrogen bonding, depend on, to some extent, the composition of the molecule. In order to have hydrogen bonds, it has to have hydrogen bonded to nitrogen, oxygen, or fluorine, which this doesn't. There's no hydrogen in the formula at all. But for dipole-dipole forces, it's determined by whether or not the molecule is polar. So this reviews back to things we learned in Chapter 4, where we have to take the formula of a compound and decide if it's polar or nonpolar. So to do that, we have to draw the Lewis structure and figure out the molecular shape and how that relates to polarity. So for SF4, let's count the electrons quickly. Sulfur is group 6, so there's 6 valence electrons. Fluorine is group 7, so there's 7 each for the 4 fluorines. So the total number of electrons for SF4, we have 1 sulfur with 6 valence electrons. We have 4 fluorines with 28 total, 7 each. All right, so this molecule should have 34 valence electrons. We arrange them as follows. We start with single bonds to each fluorine. We complete the octet on fluorine with lone pairs, so 6 more electrons per fluorine to give them a total of 8. 2 from the bond, 6 from the lone pairs. And at this point, we've completed 4 octets, so that's 32. 4 times 8 is 32. There's 2 more electrons that have to then go in the central atom. So the net result of this is that in terms of AXE notation, this is AX4E. And when we introduced this topic back in Chapter 4, we learned that any molecule that has 1 lone pair has to be polar. So if there's 0 lone pairs in the central atom, it would be nonpolar. 1 lone pair has to be polar. The structure would be called seesaw. Again, that's another detail that we would have to know for the final. But for this, we just need to know if it's polar or nonpolar. So anything with 1 lone pair is polar. So because it's polar, it will have dipole-dipole forces. Every polar molecule will experience that. Those, again, are where we have a permanent dipole in the molecule, a permanent region of partial positive and partial negative charges. Those opposite partial charges attract to each other, and so that would be what we call dipole-dipole forces, which is going to be present in everything that's polar. So 2 of these, A and C, would both be intermolecular forces for this molecule here. No hydrogen bonding, because for hydrogen bonding you need to have hydrogen bonded to nitrogen, oxygen, or fluorine, which we don't have in this molecule. So that's the type that would not be present. All right, questions on that? Or intermolecular forces in general? Yep.
Anything that's polar always is.
Yep. Yep, as simple as that. Yeah.
Then covalent bonds are intramolecular forces?
Yeah, so covalent bonds are intramolecular, meaning that they hold a single molecule together. Intermolecular forces are forces between 2 or more molecules. Yep. Any other questions on this? Okay, the last 3. This one is also dealing with intermolecular forces, but it talks about how does the intermolecular forces affect the properties. So one of the important reasons why we have to be able to predict which intermolecular forces something has and how strong they are in a relative sense is because that relates to some of the key properties. So we have 5 choices here: melting point, boiling point, viscosity, surface tension, and ideal gas behavior. Most of the properties of a liquid are going to be directly related, or a solid or a liquid are going to be directly proportional to the intermolecular forces. So melting point or boiling point, the phase change temperatures, are both going to be increasing as we increase the strength of the intermolecular forces. Because when we melt a substance into solid, we have intermolecular forces holding those molecules in place. You have to put energy into the solid to break some of those forces apart to allow them to move around as a liquid. And the stronger those forces, the more heat you have to put in, so the higher the melting temperature occurs. And same argument for boiling point. Boiling point is even more dramatic because to boil a substance, you have a liquid that's, the molecules are moving around in contact with each other. When they have intermolecular forces that are keeping them in place. In order to boil something, you have to break all the intermolecular forces to separate them from each other. And again, the stronger the forces that are holding them together in the liquid, the more heat you have to put in, the higher the boiling point. So both of those phase change temperatures will increase as the intermolecular forces get stronger and stronger. Now, viscosity and surface tension are two properties of liquids. Viscosity is how thick the liquid is. Surface tension is the resistance to increasing a surface area, which is basically the tendency of some liquids to form spherical droplets as opposed to just spreading out on the surface. And again, how strong those properties are, how much viscosity it has, or how high the surface tension is, directly related to intermolecular forces. The stronger the intermolecular forces, the more viscous something will be, and the higher surface tension it would tend to have. So all four of those directly correlate with intermolecular forces, but then ideal gas behavior is the one where the stronger the intermolecular forces, the less ideal the gas will be. So we talked about this in the previous problem, so this will be our answer. This is one that doesn't increase with the strength of intermolecular forces, because one of the assumptions of the ideal gas law is that there are no intermolecular forces between gas molecules. So in real gases there are, and if we make those intermolecular forces stronger and stronger, it's going to behave less and less like an ideal gas. And in the extreme, where the intermolecular forces are really strong, it's going to behave like a liquid, because then it's going to condense into the liquid phase. So as you increase the strength of the intermolecular forces in a gas, it's going to behave less and less like an ideal gas and have more deviations from the ideal gas law as a result. Okay, questions on that one? So that's just properties of liquids. We don't expect you to know those in really great depth, but you should be familiar with the terms and familiar how they relate to the intermolecular forces to be able to do that. All right, on to the last two. So this is the one sort of type of quantitative question that we had in Chapter 9, which is what are called heating curves, or basically calculating how much heat is required to do some combination of either phase changes or warming a substance, usually at least two of those processes together. And so for these types of things, what you have to do is think about what phase changes are going to occur, and then think about any temperature changes that would occur after that. So here what we have is dry ice, which is solid CO2, and we're going to convert it to gaseous CO2 at minus 78.5. So remember that dry ice, carbon dioxide, is a substance that undergoes sublimation. It goes directly from the solid phase to the gas phase. If you've ever played with dry ice before, well, be careful because it's really cold. But if you've ever messed around with it, you know that it doesn't melt. It doesn't form a liquid when it sits there. It just evaporates off directly into the gas phase. So that's called sublimation. So we're going to figure out how much energy it takes to do that process, and then after sublimation, once we've converted it to the gas phase, then we're going to heat it up to room temperature, 25 degrees Celsius. So this is going to be sort of a two-step process. So the first stage of this is going to be the amount of energy that it takes to sublime the CO2, to convert it from the solid to the gas. So the first step is going to be a phase change. Now phase changes occur at constant temperature, and the amount of heat that's required is going to be the amount of substance that we have times the enthalpy for that phase change process. In this case, it's sublimation. All right, and the sublimation enthalpy is given in kilojoules per mole. So that's the amount of substance we want to use, is moles of that multiplied by the delta H of sublimation. That'll give us how much heat is required to sublime that amount of CO2. So we need to find the moles of carbon dioxide, because we're giving you grams here. So the moles of carbon dioxide are, you have 25.3 grams, and 1 mole of CO2, I don't think I gave it to you here, but it has a molar mass of 44, so we have to calculate that. 44.02 for being really exact. So that comes out to 0.575 moles. All right, so that's how many moles of CO2 we have, and then so to calculate the amount of heat that it takes to sublime that amount, we have 0.575 moles. And then the sublimation enthalpy is 26 kilojoules per mole. Yep. Thank you. And then I wrote that up correct up there. So I just wrote, okay, so we're good. And then we just have 26 kilojoules per mole. So it's going to take 14.95, we can round later, kilojoules to sublime that much CO2. And then once it's converted into gaseous CO2, we're going to then warm it up to 25 degrees Celsius. And so whenever we're warming a substance, that's where we use what we learned in chapter 7, which is that the heat for that process, stage 2 as I'll call it here, we're going to heat it up from the temperature that it's sublimed at, which is minus 78.5, to the final temperature of 25 degrees Celsius. And in that case, when you're heating a substance, as we learned and used already in this review, Q is equal to MC delta T. And so we have, in this case, the mass of substance that we need, which is 25.3 grams directly given to us. We need the specific heat capacity for CO2 gas. So remember that all the different phases, solid, liquid, gas, have different heat capacities. So you have to make sure you use the correct one. Here I only gave you the one for gas, but if we had it for solid, we'd have to not use that one because at this point we've already converted it to the gas phase by sublimation. So we need to use that value of specific heat capacity, 0.819. And then for delta T, it's going to be final minus initial. So the final temperature is 25 degrees Celsius, and we're heating it up from minus 78.5. So to make sure that we get the delta T correct, so it's negative 78.5. So the delta T is going to be about 103 something positive. And so what that means is when we multiply that out, we get 2145 joules. We're looking for, I guess I didn't specify here, but the answer should be in kilojoules. This is in kilojoules, so we're going to add to that value in kilojoules as well. So I should have specified the units, but typically for these problems it will be kilojoules. So then the total amount of heat that we need is just the two added together. 14.95 kilojoules for sublimation plus 2.145 kilojoules for heating it up. And that comes out to 17.1 kilojoules. Again, I wasn't specific on units or decimal places and things like that, but that's what it would be here. Oh, we have another class coming. All right, let me just run through the last one. If we have any questions on that or anything else, just meet me outside and I'll discuss them so I can get through this. All right, here we're asking a question about a phase diagram. So we want to know which is correct. So liquid can exist below 0.6 atmospheres. 0.6 atmospheres is the triple point. That's going to take us directly from solid to gas. You don't have the liquid phase anymore, so that one is false. Point A in the diagram, only the gas is present. So here again, left side is solid, middle is liquid, right side is gas. So that one is false. Point E on the diagram is called the triple point. Triple point would be there where they intersect. This is called the critical point. So that one is wrong as well. At point B in the diagram, liquid and gas phases are both present. So point B is the borderline between liquid and gas. And so when you're at the borderline between two phases, that means you have both of them present. They're converting between each other. So this one would be true, making it choice D. All right, so I don't want to keep the next person waiting. I always forget that there's a class after us here. So come outside and find me, or I'll be right back to my office after this for a little bit if you need any questions on these last two. So sorry I had to rush through those, but I'll be around next week as well, so if you have any last minute questions before the exam, please come find me. And let's get out of here so the next class can start.